Generative AI is the technology behind synthetic images, voices, and even whole virtual worlds. Understanding how it works can help its adoption. The idea behind generative AI is that of a zero-sum game. A zero-sum game is a two-player game in which the gain of a player can come only at the loss of the opponent. Common examples are rock, paper, scissors, chess, checkers, and most two-player card games. In the specific case of generative AI, the two players are two software components called generator and discriminator that compete in what's called a generative adversarial network, or GAN. The generator tries to produce realistic data, while the discriminator tries to spot fakes. One success means the other failure. The discriminator is trained like a classifier by using real and fake data. It learns to distinguish real data from the generator's fakes. It gets feedback, loss functions, based on accuracy. In particular, the goal of the discriminator is to assign high probability to real data and low to generated ones. The generator doesn't know what real looks like. It only learns from the discriminator's feedback. When it successfully fools it, it gets rewarded. This forces the generator to improve until its outputs are indistinguishable from real data. If the generator's training process has success, the discriminator is unable to distinguish the real data from those produced by the generator. And therefore, the discriminator assigns each data received in input with 50% of being real and 50% of being fake. Once the generator's training is complete, we discard the discriminator and we use the generator giving an input some request. The process whereby the generator generates data given a query is called inference. In the specific case of text generation, the generator is essentially a predictor that is called iteratively. That is, given a portion of text, it generates a list of most probable following words and then chooses the word with the highest probability. After that, the predictor is called by giving an input the initial portion of text augmented with the word generated previously. The process is repeated until the predictor generates a special word corresponding to the end of the answer. The generator is essentially a large neural network with many parameters. The larger the number of the parameters, the higher the power of the network. However, the complexity of the training process, the time necessary, and the amount of data necessary increase as the number of parameters increases. Since big models are expensive to run, several attempts have been made to reduce their size without losing performance. Distillation is now the most known technique to do that. This lets us deploy powerful generative models even on mobile devices or in real-time systems. In particular, model distillation is a compression technique where a smaller student model is trained to replicate the behavior of a large teacher model. Instead of learning from raw labels, the student is supervised using the teacher's soft outputs, logits or softmax probabilities, which contain richer information about class similarities. This helps the student approximate the teacher's function while using fewer parameters and less computation. Distillation can be applied to classifiers, language models, and even generative models.